Thank you. So, as Alyssa said, I just defended my PhD, and I think I had a fairly unique graduate school experience in that I do a lot of field work. So I had a lot of pretty crazy adventures where I got to go a lot of amazing places really around the world. So I'm just sharing one of those adventures with you today. Let's see. So about a year ago, I was on my way to the Arctic Ocean, and on August 12th, 2018, I reached the North Pole. I was part of a large international research expedition that was jointly led by the US and Sweden, but involved researchers from several different countries, bringing together about 40 scientists working on over a dozen different research projects, and spending 2 months in the Arctic Ocean working and living aboard the Swedish icebreaker, the Odin here. So we're really, really interested in studying the Arctic because the region is dramatically changing. The Arctic is currently warming twice as fast as the rest of the globe, and are experiencing really dramatic decline of our Arctic sea ice. So this map here is showing the Arctic sea ice extent last September. September is the summer minimum each year. So to orient ourselves, let's see. So this is the North Pole here. We're looking down on the Arctic. We have Alaska, Canada, Greenland, Russia here. And our ice extent last September, shown in white, is compared to the median since 1981, which is shown in this yellow line. So we see that we've lost a lot of sea ice, particularly in areas of the western Arctic Ocean, and this trend has been ongoing for many years now. In addition to us just having less ice, the ice that remains is younger, meaning it's thinner, so it can crack and fracture more easily. And this leads to areas with open leads, which are just areas of water surrounded by the sea ice. So if we have less sea ice, more open water in the Arctic, we expect to have more emissions from the ocean surface and more ocean to atmosphere interactions happening. So our Arctic expedition last summer departed from Svalbard, which is, just come point here, this island about north of Norway. So you can see here, just east of Greenland. And this, the red track is showing our path on the ship up into the Arctic sea ice. We were looking for the ideal location to actually find a large ice floe and set up a research station. In that search, we actually made it all of the way to the North Pole. So on August 12th, we reached the North Pole. It's one of those situations where as we were going farther and farther north, at a certain point, you're close enough that the captain was just like, all right, we're gonna go. So we spent about a day at the North Pole. We collected some samples, did some science, justify being there, and then threw a big party toasted with champagne, and then actually continued on our search for our perfect research location. So in the middle of August, we reached our ideal ice floe home here, and we actually anchored the ship to the ice and then just drifted along with the sea ice for about a month while we were taking measurements both out on the ice and from the ship. So that period is highlighted here in our dark red line. So if we see our nice research station on the ice here, we have our own open lead, one of those areas of open water that we can study. And then out on the ice, we set up all sorts of different research stations to study things like the meteorology and the sea ice physics and the atmospheric chemistry. Okay. So some of the main questions we wanted to answer collectively for this large campaign were how is our sea ice loss potentially influencing the atmospheric composition in the Arctic through those ocean-atmosphere interactions. We also wanted to see if our marine biology and sea ice biology would impact the atmospheric chemistry in the region. And really why we care about the atmospheric composition and atmospheric chemistry is that, our atmospheric composition plays a large role in our climate. So by better understanding that, we might be able to improve our climate models. Okay. So a lot of our research then focused on atmospheric aerosol, or the particles that are in the air. So aerosol is defined as just any solid or liquid particle suspended in a gas. So in our case, the gas would be our atmosphere. And these particles can range in size from single nanometers to hundreds of microns. In comparison, a piece of beach sand is about 90 microns in diameter, and one single human hair would be about 50 to 70 microns. So in just a couple designations for general particle sizes we might talk about are PM10, which would just be particles smaller than 10 microns, and PM2.5, which would be particles smaller than 2.5 microns. Okay. All over the world, these aerosol particles come from many different sources. Natural sources like emissions from trees or wildfires, dust, volcanoes, sea spray from the ocean, and then also from human activity through fossil fuel combustion, our cars. A lot of these sources not only emit particles directly to our atmosphere, but can also contribute to reactive gases that are emitted to the atmosphere and then can actually chemically react with particles and create a very complex dynamic atmospheric composition. Okay. So one of the most important sources in the Arctic and what our expedition focused on is the sea spray source from the ocean itself. Okay. And just for some context, outside here in Ann Arbor, there's probably thousands of these tiny particles per cubic centimeter of air, so per milliliter of air. In really polluted places, if you think about like large cities like Beijing or New Delhi that can have really bad air quality problems, these concentrations can be much higher, and at those high concentrations pose a health risk to us. But typically in the Arctic, concentrations are much lower, maybe tens to hundreds of particles per milliliter. So we would consider this a fairly pristine or clean environment, but the particles are very important in the Arctic, particularly because of their impacts on our climate. So these particles impact our climate in several different important ways. They can directly scatter or absorb incoming sunlight, which would lead to a cooling or a warming effect, respectively. These particles can also deposit onto surfaces. So if you think of, in the Arctic, we would have a lot of bright snow or ice-covered surfaces that are very reflective. They reflect a lot of our sunlight. If you have a dark absorbing particle, such as soot, deposited on that, it'll change the properties of that surface and its interactions with sunlight. And these particles also have really, really important impacts on our climate through participating in cloud formation. So these particles can take up water to form cloud droplets, acting as cloud condensation nuclei, and they can also seed ice crystals in the atmosphere, acting as ice nucleating particles, and through both of these processes help form clouds. And through this participation in cloud formation, these particles then impact cloud properties such as the reflectivity of the clouds, the cloud lifetime, and precipitation. Okay. But despite having all these really, really important impacts on our climate, these specific processes are not well represented in our current climate models. So despite everything we know about our climate, the fact that we know it's warming, we know our main climate drivers through those greenhouse gases, and we can predict how this warming will continue in the future. There's little processes we would still like to understand better in order to make better predictions further in the future, and particularly in regions like the Arctic, where we don't have many observations. And these particles are one of those main areas that we can improve our understanding. Okay. So one of the main reasons that we still have these gaps in knowledge is that all of those climate impacts actually depend on the chemical composition of each individual tiny particle. So just as an example of that, if we considered just a simple two-component system where we had yellow particles here being some inorganic salt that's very hygroscopic, takes up water easily, and our blue particles being some more organic component that would be more hydrophobic or would not want to take up water. In one extreme, we could consider our aerosol population being what we call entirely internally mixed. So both of these components would be present in every single particle in similar quantities. While in our other extreme, we would consider an external mixture where each particle only contains either the inorganic salt or the organic component. But due to the fact that we have a variety of different aerosol sources and complex chemistry that can continue going on in the atmosphere, we know that our real world mixture is something more in between and more complicated, where we have different amounts of species in different particles, and they might actually be distributed within each particle in different ways. So then if we consider how each of these models would take up water to form those cloud droplets, we might expect that our internal mixture, all of those particles would be able to take up water and what we call activate or be efficient at forming cloud droplets. Where in our external mixture, only those hygroscopic water-loving salt particles would take up water, and the organic particles would just hang out and just not activate. And in our real-world mixture, we see that and not only does it depend, again, on the chemical species present, but how they're distributed within those particles. So in order to understand the individual particle composition and be able to predict then the climate impacts, we have to then conduct measurements of the individual particles, which is not common and can be logistically challenging. So that's why we need more of these measurements in order to inform our climate models, and particularly in the Arctic. Okay. So my main piece of this puzzle and my motivation for participating in this expedition was to then explore that potential ocean-atmosphere interaction through the sea spray aerosol in these open leads or areas of water within the sea ice. So when we have wave breaking on the ocean surface, this forms bubbles. And as those bubbles burst, they emit sea spray aerosol. So we would expect then this sea spray aerosol to be comprised of a lot of inorganic sea salts found in the ocean. But this can also be influenced by any marine biology or contributing any organic material to the ocean surface, such as in the Arctic we have large communities of sea ice algae and bacteria present. So then if we have both this organic and inorganic contribution, we might expect our sea spray aerosol to represent sort of that kind of complex mixture. So this was something we were really interested in investigating on this expedition, looking at the connections of microbiology in the water and on the sea ice to our sea spray aerosol, and then exploring how that would impact cloud formation. So there were different researchers involved were again studying the meteorology from on the ship and on the ice, deploying balloons to study the clouds and the aerosol, looking at the sea ice physics. And then we also set up a station right at our open lead site there so we could study the bubble physics in the water, study the seawater chemistry and biology, and then explore the potential for that sea spray aerosol source. Okay. So for my aspect of this project, we had three different aspects to this. The first being actually going out and collecting seawater to look at the chemistry, biology, and the physical properties. So we collected water out on the ice from the open lead with a very sophisticated method using a bucket. And we also collected water samples from the ship itself using an actually sophisticated, what they call rosette of bottles that's deployed on their CTD instrument that measures conductivity, temperature, and depth of the water as you're sampling. So we also took this water and generated sea spray aerosol from it. So we have this tank that mimics that wave breaking process. We actually deployed it outside on the deck of the ship under this tent so we could keep it cold and mimic the water temperatures that were collected, which were typically around 0 to -1 degrees Celsius during this time. So pretty chilly when you have to put it all in the tank. And then from the headspace of this tank, we sampled the aerosol produced with instrumentation housed inside our laboratory. So we had instruments that measured the number and the size of the particles produced, and we also collected particles onto filters, so then we could then take them back and analyze, again, through methods, microscopic methods to look at each individual particle and determine the composition. Okay. And then finally, we collected ambient particles in the atmosphere where we were so we could compare what we generate from the seawater to what we're actually seeing in the atmosphere in that location. So we had all of these inlets deployed off the top of the ship itself, leading into a laboratory where we again had those similar instruments to measure the particle number, size, and then later on the composition. Okay, so just very quickly, share some of our key findings related to those questions, though this work is ongoing. Throughout this whole expedition, we collected so much data that it'll really take years for the whole team to work through their different projects and really gain the fullest understanding we can from this study. But to the first point, is sea ice loss impacting our atmospheric composition? Say yes. We see that the sea spray aerosol was a significant contributor to the atmosphere. And by comparing the composition of what we generated from our tank to what we saw in the atmosphere, we see that's very similar, indicating that is an important source. Okay. Does the marine biology and the sea ice biology impact our atmospheric chemistry? Yes. When we later on analyze the particle composition, we see that these particles are greatly enriched in organics. And we could even characterize the molecular composition just of the organic component in each particle. And we saw signatures of compounds that are produced by these sea ice algae, which is actually really exciting. Okay. And then finally, can further understanding of this atmospheric chemistry help improve our climate models? Say, this would be, ongoing future work, but I hope so, because the sea spray aerosol is very relevant for cloud formation and participating in those climate processes. But understanding the role of both the organic and inorganic components would be really important in predicting that. Okay. So I'll leave you with some fun photos of our expedition here, and Alyssa will let me know if there's time for any questions.